let's talk about section 12.2, linear regression. Now, we've already talked about scatter plots, so now let's actually talk about models that actually give us the set of data that gives that regression line that we've been talking about. Now, this regression line itself is actually given a name, and it's called the least squares regression line. It is a line for which that the average amount of variations from the data is at its smallest. It's also called the best fit line. Now, basically we can say that it's y hat is equal to b sub naught plus b sub 1 x. Now, I do want to kind of give you a little bit of a memory booster here. You've probably seen somewhere along the way y equals mx plus b. Okay, now this basically is, if I am looking for an algebra class, this was what we used in algebra. Now all I'm going to do is basically b sub 0 and b itself. B sub 0 would be, if I plug in x equals 0, where do I start at on my linear regression? That's where that b is coming from. So b sub 0 is actually from there. And then b sub 1 here is not necessarily a different b value. It is actually the slope. Now, this is not a normal slope. This is not the slope that we're used to. So it's not this slope. It's not the m equals. There's a lot more to this because, again, this is what we call the best fit line. And so there's going to be the average of variations that end up happening here. Now, the slope of a least squares regression line is actually paired data from the sample, and it's given by the following. It is a very complicated formula. Now, do you need to know that formula? Heck no. Okay, so please understand that these are the formulas to get your slope of that least squares regression line, and this is how you find your b sub 0, or also known as the y-intercept for a least squares regression line. But again, I do want to point this out that these formulas, even though technically they look incredibly crazy here, you do not actually need to memorize these formulas. The calculator will give you everything you need. So to determine if R is statistically significant, it is just the first hurdle in determining and deciding whether or not a linear regression should be used to predict a value of the response of the variables itself. Now, if R is what we call statistically significant, now we can still check that the scatter plot depicts a linear relationship between these two variables. Now, what that means is R fails to be statistically significant, then the results are not meaningful enough to use, meaning that the linear regression that should not be used as a model for the relationship between these two values because R itself was not statistically significant, meaning that you did all this work, but realistically the model that you may create is just basically worthless. Okay, as long as it's statistically significant, any model that we create is at least statistically significant itself. So the local school board wants to evaluate the relationship between the class size and the performance of the state achievement test. Now, it's decided to collect the data from the various schools in the district, and the data from the sample of 8 classes is shown in the following table. Now, each pair of the data value represents the class size and corresponding average score on the achievement test for one class. Okay, now we're going to determine if there is a significant linear relationship between the class size and the average test score at a 0.05 level significant. If the relationship is statistically significant, then we're going to find the least squares regression line for the data that we have. So the first thing we have to do is decide whether the variable, which one's going to be the x and which one's going to be y. And now consider whether there is a possibility that one might influence the other. Now we were interested in the possibility that the class size influences the average test score. So that means that the class size is going to be x, our explanatory variable, because it explains what happens in the response, which will be the test scores, which is our response variable. Okay, so I'm going to go back and I'm going to put this all in the calculator. So again, this first thing we're going to start with there is actually put all of this data in the calculator. Again, this is going to be list 1 and this one's going to be list 2. Okay, so reminding you guys what we're actually doing is I stat, edit, I put all of that beautiful stuff in there, and then I want to run stat, arrow over to calculate, and then number 4, which is my linear regression. Now, again, as I did this, you'll notice one of the things is when I click calculate, it actually gives you what that linear regression is, okay? But it also gave me my R and my R squared. So these are the types of things that we want to take a peek at. And again, I do want to go ahead and write down what that model could possibly be. But before I make sure and type that as my answer, I do want to pay attention to what R is itself and determine whether or not we have at least a level of significance there. Now, again, I'm going to say with that being really close to 1, that's pretty statistically significant, but I do want to just double check to make sure how we run that, okay? So remind yourself how we did that was that before we read out the equation for the regression, we must make sure that the sufficient evidence claim works there. Now, based upon the critical value of a 0.05 level of significance, the absolute value of that correlation coefficient must be greater than or equal to a 0.707. Again, that is where we actually had to find the critical value. So this whole 0.707, do remind yourself that that comes from one of our tables, okay? It doesn't come from the calculator. And basically, this is going to come from that table 1, which is that Pearson coefficient. And we have n equals 8 and my alpha being a 0.05. And where they correspond, that's where that came from. So as long as our correlation coefficient there is greater than or equal to this, then we should be good. We do have statistically significant items here, which in our case, 0.978. So that's definitely greater than 0.707. So there's definitely enough evidence at least a 0.05 level of significance to conclude that the correlation between the two variables is statistically significant. Now, with that being said, because we've already said that they're statistically significant, we'll need to consider the shape of the data in the scatter plot itself. So looking at the following graph, we can verify that the data does happen to fall into a somewhat linear fashion, as well as the regression model that we just spit back out. Now remember that we just ran a linreg and it said it spits back out an AX plus B, okay? And again, I wanted to bring it up on the screen because I know a lot of people, they get this right here confused right here, this Y equals AX plus B, as well as this Y hat equals B sub 0 plus B1X. These again are the same exact things, okay, except for in our case here, A is B sub 1, and B here is B sub 0. And again, notice how this basically is what we split back out here. And again, that A was a negative 1.043, and again, there it is, okay. Because we have that statistically significant, we can just go ahead and basically plug in what those numbers are, and that's what we end up with. Again, the calculator does remind you of what the formula needs to be, so hopefully that is helpful. And we can see that as you were to plot them and to plot the line, they do fall pretty closely together. Okay, so a prediction should not be made with a regression model if the following happens. The data do not follow in a linear pattern when graphed on a scatter plot. So if it does not look like it's somewhat linear at all, don't even bother. 2, the correlation coefficient is not statistically significant. If it is not statistically significant, then there's basically no model to begin with. 3, you wish to make a prediction about a value that's outside the range of our sample data. Again, I cannot use that model to predict anything outside of my model range. It's not going to be perfect. And 4, the population is actually different from that from which the sample is drawn, okay? Meaning that you took a biased sample in the first place. So we're going to use the regression model that we just did here, and we're going to use it to predict the average achievement test scores with the following class sizes: 16, 19, 25, and 45. Now, what does that mean? Well, we just did all this work to figure out what our model is. And remember, we said X was a class size and Y, that output is the class average on the achievement score, right? So if I'm asking you to predict at a class size of 16, that means I'm going to plug in 16 for that X value there. Okay, and that output is going to give me 86.397, which tells me that at a class size of 16, the average test score will actually be around, that class average test score will be 86.397. Now I can do the same thing and repeat this for the class size of 19 and the class size of 25. Now you'll notice that on the class size of 45, I'm going to say something on this one. Technically, it's not meaningful to predict the value of the testing average for a class size of 45 because 45 is outside and it's well outside the original range of data. The original range of data actually was between 15 and 29. So we can only use numbers that are between 15 and 29 to be predicted on this. We cannot say that it's outside of this at a class size of 50. That would mean I need more data there to be able to use a different model. So let's try this again. So the following data list collects the selling prices of used Land Rover Freelanders and the ages in years. Now we're going to find a regression model, a linear regression model for predicting the price of a used Land Rover Freelander based on its age and years. And now, if it's appropriate, we're going to also do a 0.05 level significant to see whether or not this is going to work. So the first thing I'm going to do is, again, I'm going to determine which variable is which, and we're going to let X be the age, okay? And then how old it is going to dictate the price, so Y is going to be the response variable, which is the price of our Land Rover. So I'm going to do stat, edit, I'm going to plug all the stuff in. X is going to be list 1, list 2 is going to be those prices, and then I'm going to say stat, calculate, run number 4, linreg AX plus B. Now once I run that output will include the correlation coefficient R, as well as R squared. It will also tell me the slope of my model and my y-intercept of that model. Again, I do want to write it all down, but I do want to actually take my R into effect in just a second. Okay, so before we actually write out the entire equation there, whether or not this is actually a significant linear relationship between these two variables, I want to make sure, does it look like there is a linear relationship first, and do we have enough evidence to prove that? So here's what it looks like here, and it does look, as we look at the model, it does look like it has like a negative relationship, which is kind of what my R said. Now, I am going to remind myself that my critical value is going to be based on my alpha, which is 0.05, and then it's also going to be based upon what n is, and again, I'm going to look at a table, and I'm going to find in my table 0.632. Now, that means that basically as long as my R is greater than or equal to this number, then at a 5% level of significance, my alpha being 0.05, then we would have what we would conclude statistically significant. Now, in our case here, our R was the absolute value of it. Again, I always want to talk about the absolute value of it. 0.863 is definitely bigger than 0.632, so there is definitely enough evidence to provide us that this was statistically significant in a linear relationship between these two variables. So because it was a linear relationship between these two variables, I can just plug in what I know what my A and B were and put them in the formula, and we get basically our regression line is as follows. Now that we've created this regression line, now I want to use it to predict something. So let's use that model to predict the selling price of Land Rover Freelanders, that is a 2.5-year-old, a 10-year-old, and a 3-year-old. Okay, now you'll notice that this will be the selling price for a 2.5-year-old Land Rover Freelander and a 10-year-old Land Rover Freelander, and then on C it's a Land Rover Range Rover 3-year-old there. So the first thing you want to do is basically plug in what the X value I gave you into that regression line that you have. And then you're just doing math at this point here. So if you need to, go ahead and use your calculator here. So in my calculator, so I've just done all this math here. Oops, second load. Go back to my home screen here. I'm literally just typing in this model, okay? Go ahead and use the rounded model like they've told you to round to. And then just type in what your X value is itself. Now you'll notice I'm not putting any variables in. All I'm doing is typing straight out. Be a little careful. Don't actually type the commas in there. The calculator doesn't really know how to handle the comma very well. But it can handle the X variable being put in as a number in the home screen there, and then just hit enter and you get that beautiful number, okay? And what that basically states is that we can say that our model is going to predict that a 2.5-year-old Freelander will sell for approximately $23,407 and about 36 cents. Now again, we can do the same with all the other ones. However, I do want to make note that the original sample only talked about Land Rover Freelanders that were between the years 1 and 4 years old. So therefore, it's really actually very inappropriate to use this model for a 10-year-old model. Okay, so even though we showed something that was very statistically significant, we cannot say that it's going to work for the 10-year-old because, again, my model original range was only between 1 and 4. The other thing I note is that on number C there, it was basically our population was continuously talking about what we call Freelanders and not Range Rovers. So basically, I cannot use a different model to predict the price of a Range Rover no matter how old it actually is. Let's try another problem. So the following table gives the average monthly temperatures and corresponding monthly precipitation totals in 1 year for the Key West, Florida. So the first thing we're going to do is we're going to create a scatter plot. And I want to know, does it actually have a linear relationship between X and Y? And again, I'm not asking you to tell me what it is just yet. I want you to look at the graph itself and determine that. Once you've looked at the graph, then we're going to calculate your correlation coefficient. Sorry, it's a bit of a tongue twister. We're going to calculate that R. Once we've calculated that R, we're going to verify that that R is actually statistically significant at a 0.05 level of significance. And if it is, then we're going to determine the equation of that best fit line. And then we'll calculate and interpret the coefficient of determination, which is R squared there. And if appropriate, we're going to predict the monthly precipitation total in the Key West for the month in the average temperature of 80 degrees. And then again, if appropriate, predict the monthly precipitation in Destin, Florida for the month in which the average is, the temperature would be 83 degrees. So the first thing we're going to do is, in order to create the scatter plot, first you need to determine what X and Y are. We're going to, again, I'm going to let X be that temperature, and the temperature predict the precipitation, which will be, my Y value there. Okay, and we're going to put it all in there. And we're going to notice whether it appears to be kind of in a straight line or not, whether it's positive or negative. Okay. And one thing I do want you to see is as you take a look at it, we do kind of notice it does have a little bit of a positive linear shape to it. It doesn't look perfectly linear. Again, I'm not asking, is it perfectly straight line? Does it look like it has a bit of a straight line to it? This one looks like it might have a bit of a curve, but it does look somewhat of a straight line-ish for parts of it, and it does look like it's positive, so I would say yes. Now, if R is statistically significant, what would be that linear regression model? So the first thing I need to do is I got to figure out what R is. So I've already looked at the graph, and so now I'm going to go and hit stat, arrow over to calculate, and we're going to run number 4, linreg. Okay, now as you do that, you're going to get your R there. And again, I'm just going to write down what R is. And again, I need to determine, is that statistically significant? And that's what C is asking for. So C was asking to go and take table 1, which is found in Appendix A. It's also found in your homework by hitting the table button, and you can find the tables for the correlation coefficients. And again, I'm looking for the critical value for a 0.05 level significance. And again, make sure you note what your N is to figure this out. And in our case here, it's 0.576. Now, since we can see that our R value, the absolute value of it, is definitely bigger than the level significance for the critical value we found, we can conclude that this is statistically significant. Okay. Now, because it is statistically significant, then we can actually tell us what that model is, which again, you've already got this ready to go. When you find your R, you have the model written down already. We just have to verify, is that model usable or not? Okay. Now in E, your coefficient of determination, again, is just basically that R squared. Again, the calculator tells you what R squared it is. Now we just have to interpret it. And basically that tells me that 73.8% of variations in the precipitation can be attributed to that linear relationship between temperature and precipitation. That means that remaining 26.2% of the variation comes from some unknown source there. Okay, now that unknown source, what it could be referring to is possibly geography area. It can also be wind. So anything like that. That's what we mean by some unknown source. Now, F said, because R was statistically significant, we can use the regression line to make predictions. So F asked specifically that in addition to 80, is it within that range that I can predict my sample data? And we did notice that it was in our range, so it is appropriate to use that model that we just created. So we're going to plug in x equals 80 and figure out what our precipitation total will be for that month. So using that beautiful model, replacing x with 80, and then simplifying it out, which gives us about 2.58. So is this reasonable? Yes. It's a reasonable estimate for precipitation for the month is where the average temperature is 80 degrees. We can expect about 2.58 inches of precipitation. Okay. Now, part G says the data that was collected in the Key West, and G was specifically asking to use the model to predict in Destin, Florida. Now, please understand that these are two very different opposite areas of Florida. Destin's up near the Panhandle, whereas Key West is down near the tip. So therefore, first of all, they're not even in the same area. Second of all, the data was all collected for one area, not Destin, so it's not appropriate to use the linear regression model to make predictions in Destin. Okay, so as you're looking through all of this data, just make sure that you are double checking whether or not stuff is statistically significant before you jump into the model. And then also, as you're doing your models itself, be sure to take a look at where is all that information coming from? So the first thing I want to notice is it all in one location? And also notice the range. So in my case here, I noticed that 75 looks like to be my lowest number. And I also do notice that 90 seems to be my highest number. So as long as I'm talking about temperatures in Key West, Florida, that is between 75 and 90, I can use this model. If I talk about anything outside of this range, so say like 60 degrees, I can't use this model. That model's not going to be accurate to predict it. Again, my model is only statistically significant between the range that I originally started with.